Thank you. First, I'd like to thank you all for being here this late, and also thanks my collaborator from UC Riverside for their contribution in this work, especially Saber, who led this work. Today, I'll be presenting SpecASan, or a speculative address sanitizer, which basically aim to mitigate some transient execution attacks like Spectre, MDS, and contention-based transient execution attacks. So here we try to basically apply the memory safety into the speculative domain. At the high level, most of the transient execution attacks try to exploit speculative execution to leak sensitive data from various microarchitectural components like load store queue, line fill buffer, or L1D cache, and then leak them through a side channel. So SpecASan will try to mitigate these kind of attacks. So now to recap what is the transient execution attack, I have one example of famous Spectre V1 attack. Basically, in order to leak secret from the microarchitectural components, attacker needs to take a few steps. First, for example, in Spectre V1, it needs to train the branch predictor to make sure that it's in a state that at the time of the attack, it caused a misprediction. For example, here, he needs to provide the X less than array1 size several times, and then at the time of the attack, it provides a X which points to the secret. And from this point, we have a speculative window. So during the speculation, the first access would be access to the secret that we label it as access here. And then it may use it for some intermediate calculation, like calculating an index. And in the transmit step, it tries to transmit this secret out and then use the side channel to leak this secret. So one observation here is that like the memory safety issue that we have on the committed path, here we also have out-of-bound access during the speculation. One naive approach would be, to mitigate this would be inserting software fence after each branch. But basically, it's like we don't have a speculative execution at all, and it kills the performance. So researcher started proposing different methods to mitigate these kind of attacks while we still have a speculative execution. So as I mentioned before, in each attack we have, during the speculation, we have access, use, and transmit. Each class of attack try to prevent this transient execution attack at one memory access. For example, we have the ghost minion or Dolma, which introduce a new shadow structure into the pipeline, and they make sure that before we resolve the branch predictor, we don't bring the data from shadow structure to the actual microarchitecture. And basically, they aim to prevent this kind of attack by delaying the transmit phase of this kind of attack. The next class of attacks are Okay, sorry. Okay. I don't know what happened, but the next class is dynamic information flow tracking. In this class of attack, the aim is to basically delaying the use and transmit phase of this kind of attack and prevent the transient execution attack using these delays. And finally, we could have this software fence that basically we can insert fences before each memory access, but I mean, it has a very high performance impact. So from top to bottom, we have better security, but worse performance. So in this work, we try to answer this question. Can we have an optimal security guarantee while we still maintain the performance of speculative execution? So our key observation in this work is that basically during the speculative execution, we violate the memory safety like what we have on the committed path. For example, as I mentioned on Spectre V1, we have out-of-band access, or in some type of MTS, we have accessing data across boundaries, or we have use after free type of violation, like when we use stale data from line fill buffer. So in this work, we try to mitigate this. Instead of mitigating the side effect, we try to prevent this kind of attack by basically making sure that the secret does not propagate in this microarchitectural component. So, during the speculation using SpecASan, we could have two type of accesses, one safe access and one unsafe. If SpecASan detects that the access, the memory access is safe, then we don't delay the memory access. But if we detect that this is an unsafe access, then we have to delay the memory accesses to prevent this kind of attacks. But here we need to be able to distinguish between safe and unsafe accesses. So how can we do that? We try to extend the hardware-enforced memory safety into the speculative domain. We use ARM-MTE, and expand it to the speculative domain. So here I try to introduce the ARM-MTE or ARM memory tagging extension, the simple example. In ARM-MTE, we consider a 4-bit tags for each pointer that point to a memory location, and we set the tag for the corresponding memory location. And then on each memory access, like load and store, we check if these two tags are match or not. If it's a match tag, then we allow the access. If it's not, then we raise an exception. To expand the ARM-MTE into the speculative domain, we needed to make some modification on the pipeline. So here, the green boxes are the minor modification into the pipeline, like ROB, load store queue, LFB. We basically extend them with 1 bit or 2 bit to keep track of the tag checking status. And then the main component of the SpecASan is TSH, or tag checking status handler, which basically interact with both ROB and load store queue to keep track of the status of the tag checking. Basically, when we decode a load instruction, an entry will be allocated on both ROB and load queue, and then when the load is ready to be issued, the TSH go from initial state to the wait state and wait for the result of the tag check and data. If the result of tag checking is a match and it's successful, then the data and result will be returned to this TSH and it goes to the safe state. But if the tag are mismatched, then it goes to the unsafe state and no data will be returned to the load store queue. So here I have again the Spectre V1 attack to explain how does SpecASan can prevent this. At the right side, we have ROB and load queue. At the left, we have the data cache and the MTE tags for these accesses. So here we have the current state of this program. Let's say we are loading the array1 size here because, we consider this as a untagged access. So we mark it as a safe in the ROB. And then when we go to the spec v1 path, here the speculation window will be open and all the accesses and instructions will be executed speculatively, basically. So the first load is the one that is the one that access to the secret. So 1 in 3 on the ROB and LQ will be allocated. And when the load will be issued, it goes to the, let's say, L1 cache, and the tag will be checked. And for example, here we have tag of B, but the tag on the L1D cache for this memory location is 1. So we have a tag mismatch here, and we mark it as a unsafe access. Then the LQ will inform the ROB that this load instruction is unsafe. And because we are in the speculation window, we mark every dependent instruction after this load as unsafe instruction. And eventually we have this transmit load, which is dependent on the first load, the access load. And because, the younger load here is unsafe, we mark it as unsafe. And so the ROB will communicate with the LQ, and this load won't be issued until the branch resolved. And eventually, after the CPU realized that it was a misprediction, it squashed the pipeline, and so the ROB and the load queue. And it starts executing the next instruction from the safe path. So what we should note here is that because of the detection of mismatched tag, we didn't load any data into the microarchitectural component. To evaluate our approach, we implement SpecASan in Gen5, and we basically add the ISA extension for the empty instructions like IRG, STG, and we ran spec CPU17 and parsec for performance evaluation and compare it with Ghost Minion, which represent the shadow structured approaches, and with STT, which is a dynamic information flow tracking approach. For the security evaluation, we collected some samples of different attacks like Spectre, MDS, SCC. And as you can see, SpecASan can cover more attacks compared to other approaches. And if we combine it, with SpecCFI, then we can close almost all the transient execution attack. For the performance evaluation, when we ran it against CPU-17s, or geo mean overhead is about 2%. And when we ran it against Parsec, which is multi-threaded benchmark, or overhead is about 2.5%. And if we combine it with SpecCFI, the overall overhead would be 4%, but we can claim that it prevents almost all the transient execution attacks. For the area and power overhead, we have 0.28% for SpecASan, which, out of these 0.17% is related to ARM-MP itself, and only 0.11% is related to SpecASan. And if we combine it with SpecCFI, then we would have 0.38 percentage in area overhead increase. And for the static power, the SpecASan itself has 0.31% overhead. Combined with SpecCFI, it's 0.65%. Okay, to recap, we introduced SpecASan, which try to mitigate the transient execution attack by applying memory safety principle in speculative domain. And we think it could be a good approach to prevent this kind of attack, because we already have hardware support for MTE, and so we just need minor modification in the pipeline, and the performance overhead, and as well as area and static power overhead is, still low. And because we have the compiler, OS, and hardware support, and we believe it's easy to basically integrate this into these systems. Thank you.